Hello everyone, welcome to the third lecture. This is part A of this third lecture, and we're going to talk about mainly the polynomial functions. It also includes the power functions as well as the rational functions we're going to look at later. So let's dive in. Right. So this is what a power function looks like. It's meaning we have the independent variable, right? So it can take on any value like, and this is output, which is f of x. Now the transformation that happens inside the power function is that we have these so-called coefficients, right? So it is a constant, and we have the p here is also another constant. So the most common example is the one we have seen, which is the x to x squared, right? So it's a typical power function. And in this case, k is equal to 1 and p is equal to 2. So what this means is that we are raising x to the power of p, right? So this is a power function. And there are many other examples we haven't looked at before. So if you look at the so-called linear function, now it is also a power function because it's the raised to the power of 1, and you can also look at the cube function, the power of 3, and also even the square root or the third root of x, and this is also can be equivalently expressed as x to the power of 1 over 3, right? So this is the basic building block we're gonna use later. And of course, based on the last lecture, we can also look at the different domains and ranges of each of these functions. Now, given that, we can also look at, we have the polynomial function, which looks to be more complicated, but if we decompose, just look at this term, it is a power function, right? So we have the independent variable x, which can take on any value, and we're raising it to the power of n. So n is a fixed constant, and an is also a fixed constant. It can be 1, it can be 2, and so on and so forth. So we actually have multiple different terms here. So we have the x raised to the power of n, and then corresponding n minus 1, all the way to the power of 1, and also the power of 0. And in this case, because any number that's raised to the power of 0 is going to be 1. This is by design, and that's why we have this x to the power of 0 ignored here. So we also have these different coefficients here. So these are just a shorthand to say we have this number of coefficients. Of course, you can use any other coefficients like a, b, c, d, e, but now it's actually making it more convenient to express in this way. So a subscript n, and then a subscript n minus 1, so on and so forth. So this is what a polynomial function looks like. As you can see that it is just still a function of one variable, right? However, we actually expand it to different degree of polynomial. So this is degree of polynomial, right? So what this means is that if you look at this term, it's actually this one is the leading term, so-called, because it has the largest degree of polynomial, right? So that's why we call it the leading coefficient, which is an, and then this is the leading term. So as for n itself is a non-negative integer. It is called the degree of the polynomial of this polynomial function, right? And we have the different coefficients here. So again, its basic building block is still a polynomial function. So let's look at a few examples. So here I have still a linear function, right? And we can say f of x equals to 2x minus 2 because I'm shifting it downwards by 2 units. So this is a simple polynomial function. It's a degree of 1, right? Because the highest power is just 1. So n is equal to 1 in this case. As we can also make it slightly more complicated. So I'm drawing a function which is looking like this, right? So this function is taking the form of g of x equals to x cubed minus 2x. Now, I'm raising to the power of 3. So of course, this is becoming more and more complex, or the function is becoming more and more curved or flexible, right? So this is the power of a polynomial function. So if we increase the degree of polynomial, then the function itself is actually becoming more and more flexible in terms of the shape itself. We can even make it even more flexible. So something look like this, right? So and the form is actually can be written like this: cube 4x plus 1. So the exact form of this function is not important. What's important is that if we go from left to right, we're actually increasing the degree of polynomial, in which case the n itself is increasing, and the function with a higher n itself is actually more complicated, and the complexity is reflected as the sort of curvature of this function. So you can see as we move towards the right, then this function is actually very flexible, right? So this is increasing in flexibility. Of course, in this case, it's only 1 degree of freedom. Then the x itself is this function is just a flat line. So another thing to note is that we do not need all the terms to be present in the polynomial function. In this case, we have the degree of 3, and then the to the power of 2, this term is actually missing. So it's actually optional to have all these terms. So all these terms are actually optional. What we need is for this term to be present because it is the leading term of the polynomial function, right? If it's not there, then we cannot see the functions of polynomial, of degree of polynomial, or the nth degree of polynomial. So so there's just something to keep in mind. And yeah, I think that's it for the polynomial function. Now let's look at a few applications. Now this is a example, and what's the information here is not that important. What's important is that we have a table here. So this is to describe what happens if we increase the supply, right? The demand in terms of the available units, and the price is actually decreasing. So because if something is becoming more and more readily available, then it's actually getting more and more cheap. That's just following the supply demands relationship. Now the exact relationship, it can be expressed in this way. Usually is something to be estimated from the data, but in this case we're just given this formula. So P can be expressed as a function of x, and is just a linear function. So let's just look at the second question, because others are all for plotting purpose, which we know already that we can just take 2 points and then we can plot the line since it's a linear function. So it's asking what is the company's revenue function for this camera? Now, what is its domain? So we know that in this case, we have the revenue function, which can be calculated as the product in terms of the, so if we denote the revenue as R, right? So it's actually a function of X. So R is actually can be calculated as the number of units, right? The number of units sold times the multiplied by the price of each unit, right? So this is just the basic formula in terms of how we calculate the revenue. If we plug in, then we have X times 94.8 minus 5X, right? So this is the revenue we can get. And of course, you can see if we expand it out, right? So you can easily expand it out. X minus x squared. So this is again a polynomial function because the leading term is x squared and the leading coefficient is -5. We have this additional term here. In terms of domain, so the function itself follows the same domain as given here. So in this case, x should be living the range of 1 to 15. So this special notation here means belongs to, right? So x belongs to the range of 1 to 15 inclusive. So that's just one example of having a polynomial function, and it's actually quite commonly used in real life. All right, so next, let's look at the rational function. So a rational function is something taking this shape. So we have this an x, which is a polynomial function, and we have dx, which is another polynomial function. So rational function in this case is just the division of these two terms. So we have these two polynomials divided by each other. And that's interesting is because now we actually have an even more complex function by having two polynomial functions dividing each other, right? So now let's just look at one example. Say if I have this function called fx equals to x minus 3 divided by x minus 2. And by the way, we should have this condition, which is that d of x should not be equal to 0. And that's sort of the implied assumption, because if it is 0, then the function itself is not defined. Right, so if you look at the graph of this function, and we can draw it something like this. So this is two curves, and we'll have this dotted line here, which means that the function is actually passing through or approaching this dotted line infinitely. Let me erase this, redraw. Right, so that's one more dotted line here. And these two dotted lines are important because this is actually refers to as the vertical asymptotes, which is just saying that this is a line the function would approach if we were to let x approach, right, from left or from right. So let x approach this value, this specific value, infinitely, right? So this is the line would be approaching. Similarly for the this line we refer to as the horizontal asymptotes. So this is just two lines. Now the question is, how do we know what where do these two lines live, right? So these two lines are special, and for the special lines, we always look at what are the interesting or special values the function could take. So we know that the denominator x minus 2 cannot be 0, so x should not be equal to 2, right? So if x equals to 2, then we know that the function itself is actually goes to positive infinity or negative infinity, because now it's the value of the denominator is gonna be infinitely small. So that's exactly what we are seeing in terms of the vertical asymptote here. So that means that this point should be indicated by x equals to 2. So in other words, if we want to find the vertical asymptote, then we would let the denominator go to 0, right? And then let's say what is the value that's actually making this 0. And in this case, it's x equals to 2. But of course, there's a slight complication. We need to sort of simplify the form of fx equals to this exact form, which is the simplified version, before we can say let's dx equal to 0, and we derive what is the value of x to get the vertical asymptote, right? So regarding the horizontal asymptotes, this is actually a bit more involved, but we have a sort of a cookbook to derive the asymptote value. So let me just go to the next slide, and the cookbook goes like this. So vertical, so in terms of vertical asymptotes, we know how to get it. in terms of horizontal, then we actually have three different cases. So the first case is that we're actually looking at the degree of the polynomial. So now we still have the fx equals to nx and dx. These are the two polynomial functions, and we want to look at the degree, right, of nx, which is the degree of the leading term, and we are going to compare it with the degree of dx. Right. So in the first case, if say degree of nx is bigger than degree of dx, right? So in this case, if I just put it like this, right? So degree of nx is bigger than the degree of dx, right? So it's a slight abuse of notation. So if that's the case, that means that the denominator is actually the sort of the leading the main power, the main force of this whole term. So we know that the horizontal asymptotes is actually measuring what happens if x goes to infinity. Now infinity could be positive, it could be negative, right? So what happens in this case? If we look at the right side, that is approaching the value of it's actually 1, right? So the value of 1. And if we go to this side, it's also approaching the value of 1. So this is always look at what happens. What's the value of fx if x goes to infinity? So now if dx is the main force, then because it has a it has a higher degree of polynomial. My apologies. This should be the other way around, right? So if the degree of a polynomial of the dx function is actually higher than the degree of polynomial of the another function nx, then there's actually the horizontal asymptotes, right? The horizontal it should be 0 in this case, which means that y will approach 0 or approach 0, or can say y is equal to 0 because now x is approaching infinity. That's because, say for example, if nx is 1 and dx is x squared, right? So if x goes to infinity, then this term will actually goes to 0, right? As x goes to infinity, because x now is the leading term. And this is true even if now the denominator is x. Right. So this is actually because we have the major force in the denominator. Now the second case is that what if they are equal to each other, right? So the degree of freedom. So for example, we have the 3x cubed and 4x cubed. Now if they are equal to each other, right? So both the degree of the degree of 3, then we can actually cancel them out. So the net result of the horizontal asymptotes is actually 3 over 4, right? So this is to say that we actually only to look at the leading coefficient, right? So remember the leading coefficient is this term. So this is the leading coefficient. Right, so the an is our leading coefficient. So we just take the leading coefficients and then plug it in to get the value of the horizontal asymptotes. So the third case is the last case, which is what if n is the leading force, right? So what if n is the leading force? So if that's the case, then actually there's no horizontal asymptote, right? Not exist, and that's because imagine there's a function to say x cube and then x, right? So what's the value of this term if x goes to infinity, right? So this value itself is also infinity, right? So that's also saying that it does not exist in terms of specific value. So that's a bit abstract. Now let's look at a concrete example of this expression here. So this is our nx, this is our dx, right? We can actually do some simplification by performing the factoring we did earlier. So fx could be expressed as this way. So 3 is minus 1, x plus 2, and the bottom part will be minus 1 plus 1. So always feel free, and so you're also encouraged to do a bit of double check to, for example, expand it out. Right? So for example, this one, expand it out, see if it's equal to the original form. If it is, then you are safe in terms of performing the factoring. Now, it's obvious that we can actually cancel this out, right? So assuming that x is not equal to 1. So now fx becomes 3x plus 2, 2 times x plus 1, right? So this is the sort of the standard canonical form we can work with. Now, so in terms of the vertical, right, asymptotes, if you like vertical, then we look at making d of x equals to 0, right? So that's assuming that's x plus 1 equals 0. And that's means that our vertical asymptotes, which is the line, that's the function we'll approach when by setting the denominator equals 0, would mean that x will be equal to -1. So that's our vertical asymptotes. Horizontal. Right? So horizontal means in this case we have the x both on the same scale, on the same degree of polynomial, right? So that means that we could fall into the second case. So the net result would be 3/2, and that's because as x goes to infinity, right? These two terms actually cancel each other because they are more or less, they will become more and more close to each other. Then we can cancel them out. So the horizontal asymptotes would be 3/2, right? So that's just something to keep in mind. And yeah, so that's it for this lecture, and I'll see you in the part 2 of this lecture. Thank you.